Great. Hello, everyone, and welcome to our webinar today entitled STA 101. My name is Megan Fielding. I'm a business development manager here at C-Therm, and I'll just be doing a very quick introduction for the webinar today. My colleague Hitoshi Taniguchi, who I'll introduce shortly, will be presenting the technical content of the webinar here today. So today in STA 101, you can expect to learn some principles of STA, how to analyze STA curves, how to optimize measurement conditions, and some of the advantages on the Rigaku STA system. Now, a little bit about us here at C-Therm. We really focus on the thermal conductivity measurements and thermal analysis. But today, we're going to be really focusing on the STA, which is one of the instruments from our partners at Rigaku. We've been partners with Rigaku for a very long time. They're known really worldwide for being a leader in the X-ray analysis industry, but their thermal analysis instruments are extremely advanced and have some really nice innovations that we'll talk about here today. So again, we are going to be focusing on the STA here today. This is a combined system, simultaneous thermal analyzer, which is a combined system of TG and DTA or DSC. So my colleague Hitoshi will go a little bit more into detail about the system and about how it works. Just at a very high level here, the system can reach up to 1500 C. And you can test in multiple different environments such as air, inert, vacuum, and water vapor atmospheres. Many different add-ons that you can use for this system, such as humidity control, evol gas analysis like FTIR or MS, or even auto sample changer to allow for a higher throughput of sample testing. The system employs a horizontal triple coil differential type system, allowing for really slight mass change detection at really incredible resolution. So you can see there the spec 0.03 microgram. And again, my colleague Hitoshi will talk more about how the GTA output is converted to DSC. And he'll also talk about a really advanced novel research capability, sample observation. All right. So some folks on the line here have actually had the Rigaku instrument installed by Hitoshi, so you'll recognize him there. But for anyone who is newer, this is my colleague Hitoshi. He's part of our engineering R&D team here at C-Therm, and he's also one of our Rigaku thermal analysis installation technicians. So I just also wanted to make a note. We are going to have a Q&A at the end of this session. So if you have any questions throughout the webinar, please feel free to add them in the chat there, and we will get to them at the end. So without further ado, I will stop sharing my slides and invite my colleague Hitoshi on screen.
Thank you, Megan. Let me share my slides real quick. All right, so hello everybody. My name is Hitoshi Taniguchi, and I'll be your presenter for today. In today's webinar, I'll be going over from everything from introductory topics such as how STA works and what it does, to more advanced topics like experimental techniques that you can use to further improve your experimental data. So without further ado, let's get started. So first, I would like to go through the contents for today's slides. Whoops, sorry. I'd like to first start with some introductory topics like what is an STA, how does STA work, different configurations that you can use for STA, how to interpret measured data, experimental techniques that you can use to improve your quality of measured data, and some exciting applications that STA have been used in the various industries. So first off, I'd like to explain what is an STA. So STA stands for simultaneous thermal analysis. It's a thermal analysis techniques that is actually a combination of two thermal analysis techniques. And the first one is TG, which tracks mass changes as a function of temperature, and DTA, which tracks the change in temperature of the sample as a function of temperature. If you'd like to give a quick overlook on the properties that STA can measure, here we have STA, DSC, and TMA, which is three common thermoanalysis techniques that Rigaku provides. And as you can see, STA covers a very broad range of thermal properties that the material may have. So STA allows for a very broad characterization of a sample, while DSC and TMA is more focused on specific type of thermochemical properties. So I'd like to first start with its first component, STA's first component, which is TG. TG stands for thermogravimetry, and as I described earlier, it's a thermoanalysis technique that tracks the change in mass of a sample over a temperature range. So as we all know, some chemical reactions are associated with changes in mass. For example, a dehydration of calcium oxalate shown here is associated with a mass loss because the water is leaving the sample. And the oxidation of iron shown below that is associated with a mass increase because the oxygen is essentially binding to the sample. So these changes in mass over the temperature is plotted on TG curve shown here. And by looking at the amount of change in mass and the temperature that it occurred, we can characterize the sample over that temperature range, and we can infer what might have happened to the sample in that temperature. Although TG is a very powerful thermoanalysis technique by itself, it sometimes gives limited information as to what the sample might be undergoing at that temperature, because some chemical reactions, such as melting or phase transition, does not accompany any mass changes. So that segues nicely into the second component of STA, which is DTA. DTA stands for differential thermoanalysis, and it observes samples' endothermic or exothermic reactions that might have occurred throughout the measurement. So chemical reactions usually accompany some change in energy, some absorbs energy, or it might go through endothermic reactions, such as melting or evaporating, or some of them release this energy as it goes through that reaction, which results in crystallization or something like combustion. So this change in temperature of the sample, whether it's endothermic or exothermic, is plotted against temperature in a DTA curve. And from that curve, we can infer that the endothermic or exothermic reaction occurred during that temperature. But just like TG, DTA also has a weakness where all the endothermic and exothermic reactions will appear to be the same, essentially. So it would be very difficult to distinguish between two endothermic reactions, such as melting and evaporation, and vice versa with the exothermic reactions. However, by combining these two curves, TG and DTA, we can, the analysis of the data that we acquired becomes very simple because we have two sources of information to base our conclusions upon. For example, for the first set of curves, where TG curve is flat and there's an endothermic peak in the DTA curve, we can deduce that this is associated with melting or transition, because a flat TG curve signifies that there was no mass change that occurred during that temperature. And DTA curve, the endothermic peak in the DTA curve suggests that there was an endothermic reaction happening. So then we can infer that either the sample melted or it went through some sort of phase transition. The second set of curves right next to it shows that there was a mass decrease and an endothermic reaction happening. So we can deduce that this could have been either decomposition or reduction of sorts. Through a similar line of logic, we can deduce the different chemical reactions that might have occurred in that temperature using TG and DTA curve. All right, so now that we have got an overview of what TG and DTA is, I'd like to give a bit further look into each methodology. So first we'll look into TG, thermogravimetry, and to execute a TG measurement, you would need to track the mass of the sample and control its temperature at the same time. So it's a combined mechanism of balance mechanism and a heating mechanism. So there are two main ways to achieve this, and one is the differential configuration and non-differential configuration. So the first configuration, the non-differential type, is a configuration where only the sample is being held on in an instrument while the mass is being tracked and temperature is being controlled. So these are very simple in principle and it's very easy to set up, but it has one big weakness, and that is it is susceptible to something called a thermal drift. A thermal drift is apparent change in mass that is caused by the buoyant and convection effect of the atmosphere within the thermal chamber. So because the air or gas inside the chamber naturally moves as the temperature rises, it would appear to have some sort of mass change when there could be no mass change occurring. So this would obviously affect the measurement data, and it would sometimes give erroneous results. To account for this, differential TG configuration was developed, and there are two types of this, vertical and horizontal type. The idea behind this is that a reference, which is thermally inert, the temperature range is measured at the same time with the sample, and any thermal drift that is measured on the reference side would be canceled out with the thermal drift that happens on the sample side, since it is being measured in the same measurement atmosphere. Although the vertical type has that advantage of being able to cancel some of the thermal drift, it's more susceptible to convection effects due to its vertical configuration. However, with horizontal configuration, which Rigaku's STA 8122 employs, it allows for more precise thermal drift subtraction, and it allows for more accurate data acquisition as well, which results in less than 20 microgram baseline drift at 1000 degrees Celsius. And because of its stability, it allows for high gas flow as well of up to 1000 milliliter per minute. So Rigaku's differential TG, horizontal differential TG mechanism is equipped with a triple coil balance mechanism, which further assists with the accurate data acquisition during the measurement. So the entire TG assembly is essentially a balance where a load is applied on one side of the lever and the other side is supported by a known amount of load. The shutter is covering the light source, and at the zero, at the nominal position, the shutter would be blocking off the light coming off from the light source. But when there's any mass change due to thermal drift or change in mass, the shutter would move and change the way that the light source is being blocked, and this residual light would be detected by the light sensor. And this detection of light will correspond to activation of the driving coil, which would try to move the sample holder to its nominal position such that the light is being blocked from the light source. So on the reference side, the driving coil R would cancel out any apparent mass changes caused by thermal drift, and same amount of driving force pulled by the driving coil would be applied to driving coil S1, which essentially cancels out any of the thermal drift that has happened on the reference and the sample side. So driving coil S2 would only detect the mass changes that actually occurred, which allows for much higher precision and accuracy in terms of data acquisition. Now that I've talked about TG, I would like to shine a spotlight on DTA as well. So I mentioned earlier that DTA observes the endothermic and exothermic reactions that happen on the sample, but it does so by measuring both the reference and the sample at the same time, and it measures both its temperature and looks at the change in temperature difference in temperatures between the two. So as the furnace temperature increases linearly, the reference temperature would also increase linearly with some thermal lag due to thermal inertia. And because the reference is selected such that it is thermally inert throughout that temperature range, it would increase linearly as the thermal furnace temperature also increase. However, when the sample undergoes any kind of endothermic or exothermic reaction, it would appear as either a lag or offshoot in the temperature as shown on the plot here. So by subtracting the reference temperature with the sample temperature, we can deduce whether the sample has undergone an endothermic or exothermic reaction, and that is being plotted in the DTA curve shown below. So I've described earlier that the DTA curve is essentially a mechanism to track the sample's temperature as the measurement goes on. And any endothermic or exothermic reaction would be perceived as the peak in the DTA curve. But since DTA is more of a qualitative measurement of whether the sample goes to such reactions, we cannot quantify the degree of releasing energy that occurred during that reaction. However, by performing an energy calibration, we can convert this change in, this peak in DTA curve into peak in DSC curve, which we can calculate the area underneath the peak, or area between the peak and the baseline, and this would give the quantified energy of the reaction. So typically this conversion is done by measuring a known reference material with the known energy of reaction over a temperature range that is temperature range of interest. For example, indium has a very well-known energy of melting at the 156.6 degrees Celsius. And by measuring these known reference samples, multiple samples with such known properties, we can create an energy calibration, which allows us to quantify this peaks on the DTA curve, and we can then calculate out the energy of reaction. Once this energy calibration is created over a temperature range, we can reuse them as we measure the temperature, another set of samples in the similar temperature range. So as we can see, this is an example where indium data, which has melted at this temperature, 156.6 degrees Celsius, is being converted into DSC version. And we can see that this peak area has been converted to DSC value, and you can see that its accuracy is actually pretty high. The expected amount of energy that was released is 28.6 joules per gram, but the obtained results from the energy calibration is 28.2 joules per gram. And I'll show you later, but the creation of energy calibration is relatively simple because all you have to do is to load the metals I've shown earlier into the sample holder and measure the melting as it occurs within the temperature range. So here I'd like to show how you can load the sample into the STA 8122 unit. This is the STA 8122 unit, and the furnace would automatically open to its outermost position once you press the open button. And once the samples have been loaded, you can press the close button and the furnace would close. And once it gets to its lowest position, it would automatically stop the closing process. The one thing I wanted to highlight about that video was the sample chamber for STA 8122. So the reference side would be loaded on the left-hand side and the sample would be loaded on the right-hand side. But because of its horizontal configuration, there are no electronic components beneath, directly underneath the sample loading chamber, which has a very high advantage in terms of operation because even if you drop the sample by mistake, you can easily recover it without the worry of contaminating or disrupting any of the electrical components in the instrument. And here I'd like to show you an example of what an STA data might look like. So this is a result from an STA measurement of HDPE. This is a polymer and has been measured from room temperature up to 600 degrees Celsius. So we can divide this data into two regions. Region A, which is not associated with any mass change, but you can see that there's some thermal event happening at 136.3 degrees Celsius. And we can deduce that this is a melting that occurred because there was no mass change and it's an endothermic reaction that occurred. However, in the region B, you can see quite a drastic change in mass. There's a drastic mass decrease specifically. And you can see lots of exothermic spikes. And from that, we can deduce that it underwent some sort of thermal decomposition, whether combustion or thermal degradation in the temperature range. So now that we've talked about how STA works and how to analyze the data, I'd like to talk about preparing the measurement or the experimental techniques that goes along preparing a STA measurement. So you might think that having a sample which is small enough to fit in the sample pan is enough to run a STA measurement, but that might not give the most accurate results possible. So there are many factors to consider, such as type of sample pan to use, the method of sample preparation, the amount of sample to use, rate of heating, and what measurement atmosphere to use. So how do we know that the sample is in the optimal condition and the measurement condition that you're about to run is an optimal one? So first, I'd like to take a look at the sample pans to use. So essentially, selection of sample pan is related to the temperature range of your interest and reactivity of your sample with the material of the sample pan. For instance, as shown here, aluminum pan cannot be used in a measurement temperature above 500 degrees Celsius. So if you wanted to take your sample to 700 degrees Celsius, for example, you would have to use either the quartz pan or platinum pan shown here. And you can see that the alumina pan and the platinum pan has the same temperature range, but platinum pan has this feature or characteristics where it is catalytic, so it might induce some unwanted chemical reactions as the sample gets heated, or metallic samples might fuse into this platinum pan at the higher temperature. So although alumina pan is inferior compared to platinum pan in terms of its thermal conductivity, it could be favorable over the platinum pan because of its inert characteristics. So next, I'd like to talk about how to prepare your sample so that you get the most optimal measurement results. And essentially, sample should be should have a good thermal contact with the bottom of the sample pan for an accurate DTA measurement. So powders should be packed into the bottom of the pan with something like a steel rod. If your sample is in the block or pellets form, you should slice it such that the side that is going to have a contact with the bottom of the pan is flat. And liquids, if your sample is in a liquid form, you would want to drop it at the center of the pan and not make it stick to one side of the pan or another. So next I'd like to talk about the amount of sample to use in an STA measurement. So typical amount of sample that is used for STA measurement ranges from few milligrams to hundreds of milligrams. You can see the effects of increasing sample amount in the plot shown here. But essentially, the reaction temperature shift to higher temperature as you increase the sample mass because of its higher sample thermal mass and therefore higher thermal inertia. But although you can see this tendency in increasing temperature, the onset of the reaction will still remain the same. So if you would like to increase peak sensitivity, or in other words, if you like to look at more minute reactions, you might want to increase the sample amount. And if you are expecting very rapid thermal events happening in a temperature range, or you would like to increase the peak resolution, it might be more optimal to use less sample amount. So next I'd like to talk about the heating rate to use. And typical heating rate for STA ranges from 10 to 20 degrees per minute. And its effect is quite similar to the how the temperature range, reaction temperature shifts to higher temperature when you increase the sample amount. So if you increase the heating rate, similarly, the reaction temperature will shift to higher temperature, but the onset temperature will still remain the same. So advantage of using a higher heating rate is increased peak sensitivity. So you would be able to see more minute thermal responses. And the measurement time will become shorter because the target temperature would be reached in a shorter amount of time. And similarly, if you'd like to increase the peak resolution, using a lower heating rate might be more optimal. And lastly, the choice of your measurement atmosphere depends on type of reaction that you would like to see from a sample. So if you would like to see how sample behaves under atmosphere with oxygen, or you like to observe the combustion or oxidation of your sample, you would want to use some airflow or static air in your measurement. And if you want to see how your sample would behave in an inert atmosphere, you might want to use flow of inert gas such as nitrogen or argon in order to observe such reactions. All right, so now I'd like to talk about some of the interesting applications that were done with STA. So the first two, debinding of the battery binder material and the measurement of asteroid samples collected by NASA. This is quite an interesting one. But I'd like to I'd like to also feature some of the applications that were done with a sample observation technology. So with this feature, you'll be able to directly observe the sample as the measurement is taking place. And without further ado, I'd like to go to the first application. So this is an application where unfired anode material was measured from room temperature to 600 degrees Celsius. And as we all know, when we use a battery, it inevitably heats up due to its ohmic effect. And if the thermal characteristics of the battery material was not well known, it might lead to some unexpected consequences in terms of battery failing, or perhaps the combustion might occur in that temperature range. So as such, having a good understanding of the thermal profile of a battery material is very crucial for these kind of application. So here, unfired anode material can be observed to have a relatively stable TG curve up to 141 degrees Celsius, but uh, even at 99 degrees Celsius, the material can be seen to have already melted. And beyond the temperature of 141.7 degrees Celsius, you can see that the thermal decomposition has occurred, which could negatively impact your battery performance. So by having a thorough thermal characterization of your material, then you can uh, confidently design your components around it. So the next application is more of an exotic one. This is the case where asteroid samples from the asteroid Ryugu, which was collected by NASA's OSIRIS-REx, was measured using STA with the GCMS configuration attached to it. So GCMS stands for gas chromatography and mass spectrometry option. So as the sample was heated up and it started off-gassing, the product gases were analyzed with GC and MS technology. So the obtained data was compared with that of Ivuna meteorite, and from that, the researchers were able to determine the oxygen and water composition of the asteroid Ryugu, which allowed for rapid identification of its bulk composition. And there are not much methodologies that were available for characterizing such extraterrestrial materials. So this contributed to rapid characterization of such asteroids. And now I'd like to put a highlight on the sample observation thermal analysis capability that the Ryugu system has. And one, I wouldn't say a weakness, but one limitations for any thermal analysis techniques is that sometimes even the most experienced operators might have some trouble interpreting the obtained data simply because you cannot see the sample as it undergoes such reactions, right? Sometimes a sample might undergo a very rapid series of thermal events, but it is sometimes very hard to interpret what could be going on with just TG and DTA curves or DSC curves or just obtained data. So being able to directly observe the sample as the measurement takes place really allows for more confident data reporting and analysis of the data. The first example here is the decomposition of aspartame. And before we watch this video, I'd like to analyze the plot here without the sample observation capability. So we can see that some decomposition has occurred by the decrease in mass from the TG curve, but there are lots of thermal events going on here. And just from this curve, we cannot really tell which endothermic peak corresponds to which kind of decomposition. But by directly observing the sample as it undergoes such reactions, we can say with confidence that each endotherm corresponded to different kinds of decomposition, as we will see here. At the beginning, there's no mass change accompanied, just a temperature rise. And there's not much change that you can observe from the first endotherm, but in the second endotherm, you can see a very rapid decomposition of the sample, and it becomes this tarry substance as it reaches 500 degrees Celsius. But again, this is what the operators would see if they did not have a sample observation feature at the very end of the measurement. So after the sample has cooled down and the sample has been taken out, all they'll see is this black tarry substance in the sample pan, and we cannot tell what had happened throughout that measurement. So having the sample observation feature here is definitely an advantage. Next up, we have a interesting application where a biopolymer, PHBH, is being measured over the range of 600 degrees Celsius. So here the sample actually undergoes melting, but this peak here is very subtle, as you can see, and it goes to a very rapid thermal decomposition here. But without this thermal sample observation technology, we might not be able to determine that this little endotherm was actually a melting and not just some random bump on the table that caused such noises. Um, we have DSC and TMA instruments here, C-Therm, but very often some table bumps would cause such kind of peaks. So it is very difficult to differentiate between an actual reaction and some external noise. So this is another advantage of having a sample observation feature. And lastly, I'd like to show you this application with the matchstick head. So this is a piece of matchstick that's getting heated. And as you can see, the TGA curve is slightly trending down, which signifies some mass loss. But as described here, we can deduce that it is attributed to some drying of the moisture in the wood. And here, quite a drastic change in mass is being observed, and this is due to combustion of the wood.
Hello, everyone. We have experienced a small power outage here, but we're back up and running. Please just give us a few moments and we'll aim to continue where we left off. Thank you for your patience.
You're good to rejoin. You can rejoin. You should be able to now. Megan just told them that we had a power outage. She's back on now, so you should be able to get back in with the link I sent you.
Oh, I didn't realize.
Oh yeah, another power went out. So you've been dogging into
Hey everyone, thanks again for your patience. We're getting up and running here. Toshi is just logging back in and we'll be back up and running shortly. Thanks again. Right, I think we have Hitoshi back on screen, back up and running. I'll invite you to get your slides shared again, and we'll continue right where we left off. Just so
Right,
everybody knows, we are recording this webinar, so a link will be sent to you after. And if you would like to rewatch, you can do so if you missed the beginning part. So Hitoshi, I'll hand it off to you.
Thank you. If you don't mind, where did I cut off again? Where was I on the presentation?
You had just started the Matchstick Ed application, so
Oh, okay,
might as well
great.
just
So,
start that video over, and I think we'll be good to go.
gotcha. Just a second. All right, so apologies to those who watched it to the middle, but I'll actually start over with this presentation. So here, a matchstick head is being measured with a sample observation feature. And as you can see, in the beginning, there's not much change in TG or DTA curve, but subtle decrease in TG curve can be observed, and this is associated with the drying of the wooden portion of the match. And here we can see a drastic mass loss accompanied by an exotherm. So here the wooden portion of the match has burnt off. And we can see that the very rapid and drastic change in mass and an exotherm was observed here with the smoke coming off, clouding the camera lens. And by doing a slower playback on this region, we can see what actually happened here. But it was actually an ignition of the matchstick that occurred at that temperature. And by using the software's sample observation feature, we can extract a certain snapshots of the observation during the measurement, and you can then use that as a part of the reporting process. So here the operator is choosing the time region that they wish to extract from. So here a snapshot of the moment of ignition can be extracted, be used in further reporting. And this would give confidence in the reporting process, since we can say for certainty that this is the reaction that occurred at that temperature. And that's all I have for today. If you have any questions, feel free to leave them in the comment box below, and I'll hand this off to Megan.
Great, thanks Hitoshi. I'll get some outro slides shared on screen. All right. So thank you everyone for sticking with us through our little power blip. Just going to go through a few closing items and then we will open up the Q&A. So if you would like to learn more about the Rigaku thermal analysis systems or thermal conductivity, we have quite an extensive library of webinars and also publications and different technical resources that you can find there at our website, C-Therm.com. We've actually done similar formatted webinars to the STA 101 you watched here today. There's DSC 101 and TMA 101, which are the other two Rigaku thermal analysis instruments. So those are great resources. And there's also a webinar all about the sample observation technology if you wanted to learn more about how those work or wanted to see more applications. And my colleague has put them in the chat box there, so you can go directly to those links if you wanted to learn more about those other instruments. So upcoming webinars, our next webinar will be in a couple of weeks. It will be focused on the characterization of carbon black composites. So that is March 14th. That will be, I believe, mainly focused on thermal conductivity, but also some applications with DMA and potentially some applications with the Rigaku instruments as well. And the best place to follow us to keep up with what we're doing is on LinkedIn. We share our upcoming webinars, upcoming trade shows, or anything else there. So if you're not already, feel free to check us out on LinkedIn. And for upcoming events in North America, we have the Thermal Management Expo, which is April 30th to May 1st, and that is in Novi, Michigan. So if you're going to be there, please feel free to reach out. We would love to connect in person. And with that, I think we will close out the official presentation part of today's session and get to the Q&A. So I will stop sharing.